Howdy, this is your friendly neighborhood physics teacher here, and we're going to talk to you about geometry. Yay! It's back. Not as bad as you think. Don't stop the video. Don't you do it. Put the finger down. Don't stop the video. Promise you there's no triangles or anything in this. Just bear with me, okay? Calm down. You got this. So, geometry dealing with optics. It's actually, from the people that like to draw, I finally found your niche in physics. The ones that don't like to draw, it's okay. We have a step-by-step what to do. So it's not that bad. I promise. Just stick with me. Now, we're not going to go through the whole entire slide. I'm just going to give you the PowerPoint completely, but we're just going to go through the mirror side. This week, I'll make another video for next week that goes over lenses. But we're just going to talk about mirrors this week. So I think we'll only go through like half the slide. So we got this. So a ray of light is an extremely narrow beam of light. You really only see a quote unquote ray of light where you're dealing with like a laser pointer. But we're going to pretend like this candle produces a ray of light for what we're dealing with today so we can focus on it. What really happens is you see this light that kind of radiates outward. It radiates in all different directions. The only reason it kind of stops is there's a barrier in between that's usually some solid material or maybe even a liquid material that blocks it. And so our eyes detect light coming at it at all different directions. And that's why the room will seem bright, even though you have a light, like a lamp in the corner. Or it could be seen dim because it has a lamp in the corner because it does produce enough light. So we think we see objects, but what we're actually seeing are images. Mind blown. No, but we think we're seeing objects. We're actually seeing images, and it's because our eyes have a lens. So what we're really seeing is what we're seeing. Are we going down this route? Let's find out. Okay, so images are formed when light rays converge into our eyeballs. And so they go straight into our eyes and we see the image in the exact same spot as the object is. So our eyes are made to be like, okay, my phone's there. I can go and grab my phone, but not put it too close to my face or anything because I don't want to get attacked by microwaves. We put it back down. And the mirrors kind of work in the not very similar way because if you sit yourself and you're looking yourself in the mirror, or you can see in this pot, in the mirror, you see the pot, that's the object, but in the mirror is the image. Stepping into the looking glass, going Alice in Wonderland, you pretty much have the image that's not the object. So if you sit there and try to reach your hand through the mirror, hopefully you don't go through it and go into the looking glass. It's just an image. That's all it is. Nothing's there. If I go and look behind the mirror, there's nothing there. And so you have those light waves that converge to make an image that's not there. Our eyes are made to take the light in and to push it back so the image and the object are on top of each other. Have you ever been a little disoriented and you think your depth perception's off? You go to reach for something and you miss? It's dealing with your eyes there. Your image and your object weren't overlaying like it's supposed to. But mirrors aren't made to do that. Mirrors are made to reflect. And so we already talked about refracting and diffracting. Woohoo, words are hard today. We talked about that in our last slide. We'll talk about diffracting a little bit and refracting a little bit more later on, dealing with mirrors and lenses. But just straight on mirrors, we have reflecting. So the light hits and bounces the exact same angle, so we have incident ray, which that's just like what causes the reflection, and then you have the reflected ray, which hits and that's what bounces out. And you have your incident angle and your reflected angle. I said there's calm down. I know you're seeing angles and you're about to pause the video and freak out and run away. And you're like, there's triangles, there's side angles. I'm not going to make you do it. Calm down. Again, now we're getting a little trigger happy on me. Finger down. Watch the video. Breathe. It will be okay. We got this. We can do this. So let's keep going. And you have the normal, which your normal line is just basically like where, if you cut your two angles in the middle, it's just basically, your normal line is always like 90 degrees to your mirror. So right here, move, little sucker. So right here is your mirror, and your normal line is just always at a 90 degree, and that's just how you know it's the angles are the same. Come on, next slide, please. Or not, whatever floats your boat. I want my next slide. Next slide. Thank you. Oh, nope, too much. Nope, okay. So mirrors reflect all the different light rays. I thought these light rays moved. Sorry, that's why I was like, wait, they're supposed to move. And so you have light that's radiating outward, but as soon as that hits, it's going to reflect. And so that's different ways on how the mirror works. That's how you get the image on the other side. So it hits, your eyes see it, and then from your eyes, if you notice, which they should, oh, okay, you get these lines that are called sight lines. So you have lights that hit, reflect into our eyes, but what we're seeing is actually if those lines were straight, and that's how the image is formed. So these are imaginary lines or sight lines. So these lines do not exist. That's why we do it as dotted lines. These things do not exist because sadly enough, we can't go into the looking glass to follow Alice, not without some medical help, which we're not going to go into there. And so, but that's the different types. Like, so a window is opaque. You can look out a window and see the grass, and you're seeing the image and the object laying on top of each other. But a mirror, you have that reflection aspect of it. Oh, and the thing is over words again. You know what? Just go away. So your real image are formed through light waves, and then you have virtual image that are formed through sight waves. Your real image, again, is when your object and your image are laid on top of each other, and you can sit there and pick up your phone. Virtual images, it's like you can't sit there and reach through the mirror and grab your object. It's just the image. It's not really there. So plain flat mirrors are pretty easy to sit there and figure out. And you just draw your sight lanes. And so you do have your height. So you need to know how tall your object is and how far the distance is from the mirror. The cool thing with flat plain mirrors, your image distance is the exact same distance and the exact same height. If you sit there and you're checking yourself out in the mirror, you want to know exactly, okay, is this my eye makeup doing okay? Is the line straight? You want all that. You want it to be fine. That's when you get into those fancy makeup mirrors or the funhouse mirrors that sit there and change you get into concave, convex, and sits there and changes, makes it bigger, makes it smaller, and stuff like that, which we're about to get into, when the height and distance changes. But for just plain flat mirrors, it stays the same. So we're getting into some spherical mirrors now, dealing with concave and convex. And basically, it's just part of a sphere. It's either this side or that side of the sphere. Your big C is, of course, the center point of the sphere. If you sit there and actually drew out the whole entire circle of what the mirror would look like. And then you have the radius, which is just from the center to the edge of the mirror you're dealing with. You have your focal point, which is in the middle between your center point and your edge of your mirror. And your focal distance is from your focal point to your mirror. So focal point is just half your radius. And all this comes into play in a nice little equation. But, so you're concave or caved in. So think about if you go and reach, you can physically put your hand kind of into the mirror. It looks like a cave. You can step into it. And when you're dealing with mirrors, you have the real side and you have the virtual side. Remember, you have, the world we live in, then you have Allison's world over here. And your optical axis, again, is just an equilibrium that it makes a perfect 90 degree here. You have upright and inverted, and we'll get real side and virtual side. We'll get what that means when we start drawing our images. So, when you have your rays, you always draw them through the focal point. No matter where you're coming from, it always goes through the focal point. So you'll draw, your rays always come at a straight line, and then when you sit there and you draw them, which if we were in real class would make you draw them, you would sit there and take your ruler and you would draw it through your focal point. Now, these are all on the real side, so these are all your real rays. These rays actually exist, but we want to know what it looks like on the virtual side. So that's when you start producing your sight lines. Whoops. You start producing your sight lines, and wherever they hit and reflect back, you start doing your diagonal sight lines. Now, here is a step-by-step how to find your image using a mirror. So from the top of the object, draw a straight line. And then, so panel to the optical axis to the mirror. And then from the mirror, where you end at step 1, draw a diagonal line that crosses the focal point. And you're going to do it on both sides. So you're going to do your real side and your virtual side. So let's just see how that looks. I'm going to do a lot of back and forths. So we're going to draw a line there and there. So straight to the mirror through the focal point. But we also need to draw on the virtual side. Get some water. I'm talking a lot. So you have your straight line hitting the mirror, going through the focal point, but then you have your virtual side, your sight line that, if you look in the mirror, that you think you see that. So that's step 1. So that's or step 1 and step 2. So step 3 is from the top of the object, draw a diagonal line that crosses the focal point to the mirror. So now, instead of hitting the focal point last, you're going to hit the focal point first. And then you're going to draw a straight line out. And that's what I was trying to do. So remember, that's step 1. Then you have step 2 that is the diagonal line up. Now this gets to step 3. So you're going to draw from the top, go through the focal point, hit the mirror, and then a straight line out. And you're going to do your sight line there. Where these two lines cross, is where your image is going to be. So this is where you can get some funny upside down craziness. And actually concave mirrors is what they use if they made holograms, is what they would use to make holograms. So right now, what you're seeing, your image is going to be on the real side. So it actually is on the real side. And it's going to be upside down. So if you were looking into a concave mirror, you actually wouldn't, you would see an object that's upside down, and it would put the image on this side, on our side. So that's why if you're looking at a concave mirror and you're like, I don't see myself, it's because it's not on the virtual side. You can only really see it what's on the virtual side. Oops, I didn't mean to. You can only really see it what's on the virtual side, because you can see it in the mirror. But they actually make, concave and convex mirrors actually make real images. And so concave would be the best way to make a hologram. So yeah. So, and just where the two lines cross, and then you just draw the image to the edge. So this would be a real inverted image. So when I ask you, is it real or virtual? Real is on the side that we live on. Virtual would be on the other side, would be Alice's side. Upright would be on top of the optics axis, and inverted would be on the opposite side. So let's try that again. So remember, step 1, you draw a straight line from the top, diagonal through the focal point, straight, diagonal. And so those are real lines. We have to draw our sight lines. And then we go diagonal through the focal point. So this one's a little weird because you're like, but the focal point's and your image is in front of the focal point. You still do the diagonal through the focal point, kind of like that. And then so like again, that diagonal, that dot there doesn't really exist, but you just use your focal point to line up your diagonal line straight out, and then you have your virtual line. So where would the image be this time? Dun-dun-dun-dun. So that's why when you see girls doing their makeup, or boys doing their makeup, or anyone doing their makeup, you sit there and you see them getting really close to their mirror. It's because they're wanting to zoom in on, I was imagining looking at my eye. You want to zoom in on the object because it gets bigger. And now you actually can see it in your mirror because it's on the virtual side. So this would be a virtual upright image. So concave mirrors only work when you're up close. They don't work if you're far away. Now it's your turn. So this is and I understand that it's labeled as a concave. We usually just do a straight line. So again, step one, you're gonna draw a straight line. So step one, you're gonna draw a straight line, and then you draw a diagonal line through the focal point with putting your sight lines in the same direction, just continuing your sight lines. And then you're going to do a diagonal line through the focal point, a straight line out through the sight lines. And you get that your object is an inverted real inverted object. And what you'll notice is when you're dealing with concave, if you're behind the focal point, it's real and inverted. If you're in front of the focal point, it's going to be upright and virtual. Hint, hint. If you're at the focal point, you're not going to be able to see anything. Now, convex mirrors. Now, convex, you curve out. Your focal point is actually on the virtual side. So concave, your focal point's on the real side. Convex, your focal point's on the virtual side. Everything else kind of stays the same. So this one, you'll notice that your lines diverge. They spread out. Instead of converging, they kind of diverge. But they all converge at the focal point. Kind of cool, huh? Again, you have your sight lines that they still, still converge through the focal point. That's why it's called a focal point. So again, to do you're following the exact same steps. So straight line in, reflect again you're diagonaling through the focal point. But in this case, your focal point is on the virtual side, so it becomes a sight lines. So again, now you're on a diagonal to the focal point. Again, some of it becoming sight lines and straight out. Now, what I don't want you, if you notice, I did not do the ... to the focal point. That is not part of trying to figure out where the image is. You're just using the focal point to line up. That's all you're doing. What you want to make sure you draw is, after you hit the mirror, what that sight line would look like. And so your image would be a virtual upright image. Let's try it again. So straight line. So you draw a straight line to the mirror, and then diagonal line through the focal point. Diagonal through the focal point, stopping at the mirror, and then straight line out. And again, you get your image that is virtual and upright. Lenses and mirrors does have an equation. It's not that bad of an equation. It looks scary because of fractions. So again, no running away. I promised you no angles. I didn't promise you no fractions. But we got this. So remember, little f is your focal length. So remember that's half of your radius. Your di is your distance, your image distance from the mirror, and your do is your object distance from the mirror, or lenses, but we haven't talked about lenses yet. You can tell how something magnified, so that's if it's bigger or smaller, by using your height of the image and object and distance from your image and object. And basically, if your magnification is negative, that means it is inverted. And I will do another video on using those equations for you for Thursday, because you have some calculations on Thursdays. So refraction is when light is bent. We kind of talked about this. Remember the pencil in the water. Try it out. Get a cup of water, stick a pencil or anything in it. You can see how it does bend because your speed of light changes. So your light is bending. Now, your angles are still the same. It's just slowed down through, well, in this case, glass, because it's a solid. It slows down a lot. Your liquid slows down just a little bit. And so that, again, is refraction, just the bending of the light. Now, we're going to stop here. We'll pick up lenses next Monday. Hopefully you have a wonderful week. Remember, you are loved and appreciated. Have a wonderful day. Bye.